Another problem, finding the directional derivative of our function at the given point in the direction indicated by the angle theta. So here we can visualize our directional derivative, or understand it, I should say, a little bit deeper. So here we have our three-dimensional system. If we have a surface in 3D, some generic surface, I like to always draw this kind of surface. It's just something I'd like to visualize with. If we have our point, obviously it's a point we can specify in this xy plane, some point, and we want to find the slope at that point. There's infinitely many slopes that we can choose from, but we obviously can specify, or we can restrict in the direction of x or in the direction of y, but obviously that's very restrictive. So we can use the idea of vectors and the direction to find the slope at in a certain direction specified by the vector. So given all this information, let's figure it out. So the directional derivative in the direction of our vector, unit vector u, of our function at xy is going to be the gradient at xy dot producted with the unit vector. Okay, so given this information, we can figure out first our gradient. So our gradient is the composition of all directional or all partial derivatives. So it's partial derivative x with respect to, partial derivative of our function with respect to x, and then partial derivative of our function with respect to y. And then our unit vector is just the cosine of our angle. It's the vector, with the x component of our vector being cosine of theta, and our y component being sine of theta. It's very simple, so it's just a lot of mechanical work, but we will do problems where there isn't the angle, it isn't just the angle that's specified. There's also other information such as, other problems. We'll see. So basically, we can first think about the gradient. So our gradient of our function. So first of all, we need the partial derivative with respect to x, which is treating y as a constant, but this is going to be very similar for both of them. We can just do 1/2 times 8x plus 9y raised to the negative 1/2 multiplied by the derivative of the inside, which is treating y as a constant. So this is actually just 8. It's very similar with respect to x, except we have times 9 instead. So all of this is the same, times 9, which we can express as 8 over 2 square root 8x plus 9y. And this is 9 over 2 square root 8x plus 9y. It's the same thing. Exact same thing, except with 8 and 9 being different. So we can write this out here. So it's just 8 over 2, which is 4. Just realize we can simplify that. Okay, so that's 4 over the square root of 8x plus 9y, comma, 9 over 2 square root 8x plus 9y. Let's find the gradient at our point 9, 1. That's just going to be, so this is a 4 but not a y. It's a 4. 4 over the square root of 8 times 9 plus 9. That's going to be factoring out a 9. We can get 9 times 8 plus 1, which is 9 times 9 is 81, which is, all of this becomes 9. Square root of 81 is 9. And this is also square root of 81, which is 9. And then the 9s will cancel, so it's 2 times 9. 9s will cancel, so it becomes 1/2. So this is our directional derivative. Not our directional derivative, our gradient at 9, 1. And then unit vector is the cosine of negative pi over 6, comma, the sine of negative pi over 6. The cosine of negative pi over 6 is the square root of 3 over 2. This is negative 1/2. Sine of negative pi over 6 is negative 1/2. We can find our directional derivative now. So the directional derivative, the direction of our unit vector or function at 9, 1 is the gradient of our function at 9, 1 dot product with the unit vector. So gradient at 9, 1 we figured out to be 4/9, comma 1/2 dot with unit vector, which we figured out to be the square root of 3 over 2, comma negative 1/2. So this is just 4/9, comma times the square root of 3 over 2 plus 1/2 times negative 1/2. So this is just 2 root 3 over 9 let me make sure that I can't do anything else with this. Yeah, that's good. Minus 1/4. I think this is a good answer. I don't know if you want to combine these. If you want to, you can, but I don't think that's very necessary in this situation. That's our slope and the direction of our unit vector of our function at the point 9, 1. And that's it.